Continuing on, if I do the power regression on the calculator between list 1 and list 2, this 10.3123 is this 2052 point roughly 59. Notice that, and it has times x to the b power. There's my little b, and I've just done some rounding. And notice that correlation coefficient. And the thing that we need to again understand as AP statistics students is this little r is always a linear correlation coefficient. And you go, yeah, but this is not a linear model. Well, that's because this model came from a linear model. This model comes from the linear model between the log of the independent variable and the log of the dependent variable, and then algebra transforms it into a power function. Now the last thing I want to review is a residual plot. And when I ask you to draw a residual plot, the residual plot is going to be dealing with the two variables which you are finding a linear relationship between. So when we were dealing with the best model thus far is this power function, and the power function came from linearizing log of x and log of y. So I would want to draw a residual plot that is dealing with log of x versus log of y. So let me go back here to begin with and get that linear model between log of x and log of y. List 3, list 4. Okay, so there was my linear model that I had up here. Now I want to see how the observed log of y value versus the predicted log of y value, which I'll find in a minute, how they differ. So I have my table ready, and I need to find my residuals. So I have to find what the the predicted log of y values are for this setting, because we'll be doing a difference between these momentarily. And so I need to use the equation, and I could either type in this 3.3123 plus, let me get this down here. I could either type this in, hand type this in, or I'm just going to do the good old-fashioned variable statistics EQ, and I'm going to get that equation. And notice that I'll cursor all the way to the front. There's that 3.312, and we really have overkill of decimal accuracy here, so we could go with a rounded off version, but might as well use it. Now, I need my independent variable to be not x, not list 1, I need it to be the log of x. So I can either hit log of list 1, or I can just have this be list 3. And hopefully that works without the multiplication. Looks like it did. Okay, so here I have my log of x, I have my log of y in my list 4, and now I have the predicted log of y's here. And so I now need to subtract those to find my residuals for the log of y's. So we'll have list 4 minus list 5. Okay. And so these are my residuals. So I'm a little high, little negative, negative, high, and negative. And I'll just quickly look at my residual plot. And I actually graphed it here as a hard copy, and I believe I can include that on yours. But I could have that shown on my calculator as well. If I go to Stat Plot, now my independent variable that I have is my log of x variable. So I would actually want this to be, I believe that's list 3. And then my residuals are in list 6. And then if I hit zoom number 9, here is a hard copy of my residual plot, and here's obviously the plot from the calculator is going to mimic it as well. So we know that linear models between x and y naturally are important, and we can find correlation coefficients to describe the strength of that relationship. Exponential models really come from a linearization. They come from linearizing x versus log of y and then doing algebra to transform it into this model. So when you do a linear regression, you'll end up having like log of your y variable equals, and there'll be some constant, I'm going to call it a capital A, plus there's going to be some slope. You'll end up with some linear model that will look like this from having the linearization between x and log of y, and there'll be some type of a correlation coefficient that's corresponding to that. And then you'll do algebra and you'll be able to transform it into this type of a model. On the other hand, when you find the linearization between log of x and log of y, you'll end up with a model that looks like this. Here's your independent variable, there's your dependent variable. There'll be an r value that's associated with it, and you'll be able to do algebra on this to transform it back into a power function. And those are the only types of models that we will look at as far as where they come from. There are all kinds of other regressions on your calculator. If you look at the regression, you have quad regression, cubic regression, quartic regression, natural log regression, logistics, sinusoidal regression. So there are all kinds of regressions, and there's more than that as well. It's just that's all that this calculator does. So now you're ready to try on your own.